Algebra 2, lesson 8.6. We're solving exponential and logarithmic equations beginning on page 501. Example number 1 says to solve 27 to the 2x is equal to 9 to the x plus 2. Notice these bases are not exactly the same. 27 is not exactly the same of number as 9. However, we do know that they share a root. They both share the root of 3. The way you can tell is if you look down on that chart I made you, look down and see where, um, or look from the left to the right, and you can see where 9 and 27 are both on the third root. So what we're going to do is we're going to change both of their bases to the number 3. So 27, its base is 3, and 9, its base is 3. So that's what we're making both of them. 27, its base when you raise it to the third power, 3 to the third power is 27. And 3 for number 9 when you raise it to the second power. So you could change both of the bases to 3, making one 3 to the third power, the other one 3 to the second power. Okay. When we do that, since they have the same base, we can eliminate that part of the problem. So when you eliminate that part, or even before we do that, multiply or use the power property or the power of a power. Anytime you multiply a power of a power, you raise a power to a power, you multiply them. So 3 times 2x is 6x, and 2 times x plus 2, you distribute it. 2 times x is 2x, and 2 times 2 is positive 4. So now you have the same bases, and this is what I was saying a second ago about eliminating them. Since this is 3 and this is 3, that's what we were trying to do. We were trying to make them the same. We could eliminate them and cancel them out. Once you cancel them out or you equate the exponents, now you have a simple algebra 1 equation just that has variables on both sides. You have 6x is equal to 2x plus 4. So the first thing you do is you subtract 2x or you move it over to the larger 6x side when you subtract 2x. But I took 2 steps at once. But you would get 4x is equal to 4. And when you divide by 4 on both sides, you get x's value, which is 1. So this is solving by equating exponents. So then it says to check it to see if 1 is correct. So just plug in 1 where x's value is. Instead of 27 to the 2 times x, or to the 2x, 27 to the 2 times 1. And instead of 9 to the x plus 2, it's 9 to the 1 plus 2. So 2 times 1 is 2. 27 squared is 729. And 9 to the third power is also 729. So 729 is equal to 729. So what you're trying to do with these is you're trying to get them to have the same base. Once they have the same base, eliminate the base, and then solve the simple, what I call algebra 1 equation. Off to the side, I know you don't have a lot of room on the back, so off to the side, solve this one. 2 to the 4x is equal to 32 to the x minus 1. Again, make them both have the same base first. Take about 45 seconds on that one. Okay, for this one, you're not going to be able to change that base of 2 for 2 to the 4x. So we're going to make both of them into a base of 2. So we want both of them to be 2. So 2 to the 4x, that one's not going to change. That one's going to just say 2 to the 4x is equal to, in order to get to 32, you need to raise 2 to what power? Again, look at your chart. Just on the left, go to 2, and just scroll over to the right until you hit 32. That's 2 to the 5th power. Is the same thing as 32. 2 to the 5th power, and it's still being raised to the x minus 1. So distribute it. 5 times x is 5x. 5 times negative 1 is negative 5. So it's still 2 to all of that, and it's still 2 to the 4x power. Now notice again, both of your bases are the same, 2 and 2. So you eliminate them, or you equate the powers. 4x then is equal to 5x minus 5. And again, all of these steps are not necessarily, you might not have to write that step that I just wrote. Most people don't have to. But now it becomes a simple, again, algebra 1 equation. Typically we would move our smaller 4x over to our larger 5x side. But since there's a negative 5 over there, it's probably easier to bring this one that way. It's positive 5x, so subtract it. When you do it there, do it here. So when you subtract it on both sides, 4 minus 5 is negative 1x is equal to negative 5. And then when you get x by itself, you divide by negative 1. You do it here as well. Negative divided by negative is a positive 5. X then is equal to 5. And you could check again by plugging a number 5 in. Um, 2 to the 4 times 5 will be 2 to the 20th power. Is that the same thing as 5 times 4, 20, and 5 times negative 1? I'm sorry, 5 times 5 would be 25, and 5 times negative 1 is negative 5. So you get 2 to the 20th power on both of them. You don't need to get to that big number. You know, it says the exact same thing on both sides, 2 to the 20th power. X then is equal to 5. Example number 2 is taking a logarithm of each side. Now look at the difference between this one and example number 1. We can't change these to have the same base. Because there's no base that is the same, or there's nothing that they share. There's no root that 4 and 21 share. Now, again, before this lesson, before we had our break, we said, well, what if we have to change the bases? So right here it says 4 to the x is equal to 21. Write the original equation. And then, since the variable is on the left side, and it says 4 to the x, you want to take the logarithm base 4 of that side. So whatever that says, since it says 4 to the x, that's the reason we take the logarithm base 4. Remember, if you do something to one side, you do it to the other side. Remember, you can add any number you want to an equation. You could multiply. You could subtract anything you want. But anytime you do it to one side of an equation, you have to do it to the other side to balance it. That's why we can take the log base 4 of both sides. And again, we get the log base 4 from the fact that it says 4 on that side. And 4 is being raised to the x power. Since now it says the log base 4 of 4, we could cancel that and that. Once we do that, we have something that simply says x is equal to log base 4 of 21. Now, just like the bell work, we have two things again that there's no root that they share, but it's simply written as log 21 divided by log 4. Remember, whatever the base is at the bottom. So this is the change of base formula. Log 21 divided by log 4. And again, you're going to get a decimal equivalent, which is 2.196. It says to check that in the original equation. Again, that's not the easiest thing to check. But if you take 4 and you raise it to 2.196, which a calculator can do easily, you're going to get something very close to the number 21. And the reason it might not be exactly the number 21 is because that is a decimal equivalent. But 2.196 is what x is equal to. Let's do the same thing again in the margin with this problem. Solve 4 to the x is equal to 15. And again, look at the example as you get stuck. Again, take about 45 seconds on that one. It went a little bit longer than 45 seconds, but again, this one's just like the example. It even uses the same number 4. So right here, log or solve 4 to the x is equal to 15. Since the variable x is on the left side, since it's right there, that's the base you want to use. Log base 4 of 4 to the x is equal to, again, log base 4 of 15. So all we did, the only thing we added to this problem is we took the log base 4 of both sides. It still says 4x is equal to 15. Since we have the same log base 4 of 4, this can now cancel out and leave us with just the variables, which is what we want. Now it says x is equal to log base 4 of 15. Now again, you have two numbers that they don't share a root. Had this said log base 4 of 16, we can come up with a lot better number to go with this. But we don't have that luxury. So simply we push in, or we write it as log of 15 divided by log of 4. So log of 15 divided by log of 4. And when you punch in log 15 divided by log 4, again, make sure you use parentheses as necessary, you get x's value, which is equivalent or close to the decimal equivalent, 1.953. Go to 3 decimal places just to keep it consistent with what we did with our bell word. 1.953. And again, if you raised 4 to the 1.953, you 4 and then hit that little caret button, you're going to get a number very close to 15. It might not be perfectly exactly 15, but 1.953 is not a perfect exact number. It's a very close decimal equivalent. Okay, so this is like a one-step logarithmic equation right here. I'm sorry, this is a one-step exponential equation. We created it, we made it a logarithmic equation because we had to change the bases. What we have for example number 3 is a two-step or something that's a multi-step. You learned in Algebra 1, you learned how to undo addition, subtraction, multiplication, and division by using inverse operations. You also learned in order to undo the square root of something, you square it, and vice versa. So we learned how to undo exponents and radicals. We're going to do the same thing with this. These are in the exponent's position. Remember, when you undo things, you work your order of operations backwards. Instead of please excuse my dear Aunt Sally, you go backwards. You look for subtraction and addition first, then multiplication and division, then exponents and radicals. That was the thing that we added. And then finally, what's in parentheses at the end. And remember, parentheses is not just the parentheses themselves, but it's brackets, it's fraction bars that make grouping symbols, anything that's a grouping symbol. This one says 3 to the 5x minus 2 plus 2 is equal to 6. The difference between this one and the last example is that plus 2 part. So right here, the original equation, 3 to the 5x minus 2 plus 2 is equal to 6. Order of operations says we undo plus 2 first. So this is simple. Undo plus 2 by subtracting 2. It says plus 2 right there. We simply minus 2. And again, if you do it to one side, you do it to the other side. Now it says 3 to the 6x, I'm sorry, I keep saying 6, 5x minus 2 is equal to 4 now because we got rid of the plus 2 part. Now, the variable x is on the left side where it says 3 as the base. So what we want to do, just like example number 2, is we want to take the log base 3 of both sides. And again, the 3 comes from the fact that that's where the base is right there, 3. So log base 3 of both sides. And again, whatever you do to one side, you could always do to the other side. Now, since you have the same base as what the log's taken, this can cancel this and leave you with 5x minus 2 is equal to log base 3 of 4. That was the goal, to get the exponent down from the superscript, to get it from the top and bring it down where we could solve it. Now again, you undo your order of operations. It says minus 2, so you again go back to the Aunt Sally part. Add 2 to both sides. So when that minus 2 goes over to the other side, notice it becomes right here positive 2. So it says 2 or positive 2 plus the log base 3 of 4. And then again, x is still not by itself. X is still multiplying by 5. So you go from the Aunt Sally part to the my dear part, the multiplication and division part, and you divide by 5. Now, dividing by 5 is the same thing as multiplying. Right here it says 5x is equal to 2 plus log base 3 of 4. Dividing by 5. Everybody understands that you can divide that side by 5. That is the same thing as multiplying by the reciprocal 1 over 5. And the reason that matters is because we don't know what log base 3 of 4 is. Not yet. So if you multiply the left side by 1 over 5 and you multiply the right side by 1 over 5, remember that's the exact same thing as dividing it by 5. You have x is equal to 1/5 times 2 plus log base 3 of 4. And then it says use a calculator. Now, we have we have to change this. Most of us can't just punch this in just like this in a calculator. Most of us can't do that. We have log base 3 of 4. So it winds up being 1/5 times 2 plus, and then another parentheses, log 3 divided by log 4. That parentheses closes, and then you close it again. So try that real quick. Try to punch that in, those out there sitting there with a calculator. 1 over 5, open parentheses, 2, plus, open another parentheses, log 3 divided by log 4, close parentheses again. And when you do that, you should get 0.652. If you don't, try it again and see if you could figure out what you did incorrect. What's not exactly like I have up here. So the solution is about 0.652. Check it algebraically by substituting into the original equation, or you can check it graphically if you have a graphing calculator by graphing both sides of the equation, observing that the two graphs intersect at approximately 0.652. We'll talk more about that as we need that. Just focus on the algebraic part, not so much the graphic part. Let's try another one that's just like this one. Solve 5 to the x plus 2 plus 3 is equal to 25. Again, work your order of operations backwards, and then get to where you can plug in the calculator strokes. And then if all we're having is a calculator issue, we'll get that figured out together. Take about 1 minute on that. Okay, let's take a look at it. When you first look at this, when you see 5 and you see 25 on the other side, and you think maybe we could change the bases and make them both a root of the number 5. You can't, though. If you did that, you were at least thinking logically to an intelligent point. But the fact that there's a plus 3 right here messes that up. You have to undo that first by subtracting it. When you do that and do it here, you get 22 on that side. So it no longer says a base or root of 5. So wherever your variable is, it's on the left side right here, 5 to the x plus 2, you want to take the log base 5 of both sides, since it says 5 to the x plus 2. And we'll do the same thing on this side. We'll take log base 5 of now 22. So this cancels this and leaves you with x plus 2 is equal to log base 5 of 22. And again, to get x by itself, you undo the fact that it says plus 2 by subtracting it. If you subtract it on the left, you subtract it on the right. Now, you can't subtract it from the number 22 because it's not 22. Just as if it had said 2x or 22x, you can't take it away from that. What you can do, however, is write it as negative 2 plus log base 5 of 22. So it's x is equal to that. And if you punch in that negative 2 plus log base 5 of 22,